section 2.1 is talking really the first real descriptive statistics we're going to be looking at. And so it's talking about how do we take quantitative data and kind of condense it into a summary that you can actually look at and you can figure out what that data looks like. Basically, what a frequency table or a frequency distribution does is we're condensing the raw data. So we're grouping our numerical data into classes, is what we call them. But really, it's just an interval range. So basically, if my data runs from 1 to 30, then I'm going to group it, in this case, by 5s. So that it makes it a little bit easier to see. So instead of seeing however many individual data values all those add up to be, instead of seeing a long list with a bunch of individual numbers, right? Now we're kind of grouping them together so we can see, okay, most everybody for whatever this data set what represents falls between 16 to 20 and 6 to 10. That's where most everybody's going to fall at, right? So that's really the advantage of combining this data like this. It's going to help us see where most of our data values fall. So what the frequency is however many data values fall into that class or into that category. So for example, this is telling me there are 8 data values that lie between 6 and 10. So what your lower and upper class limits are, those class limits just tell you the class starts here, the class ends here. So every data value is going to be somewhere between 26 and 30 for this bottom class, for example. That's all those class limits mean. And then the class width is the gap from one lower class limit to the next lower class limit. So be careful. Your class width does not go from lower to upper. It goes from lower to the next lower. All right. So be careful with that. That's one of the bigger mistakes I usually see. Basically, the first thing to figure out is how many different boxes or how many different classes you want. So usually there's going to be somewhere between 5 and 20 classes. Too fewer than that or too many classes, then it really gets hard to figure out patterns in the data. So think looking for those shapes. So thinking about symmetric or bimodal or uniform. If you have too many classes, you can make any data set look uniform. If you have a class for every single data value, right, then that distribution can look uniform. So for this class, I'm going to tell you how many classes to use. So I'll always say, for example, use 5 classes or use 7 classes. So I'll say that with the problem. So you don't have to worry about figuring out how many classes to use. So from there, you want to figure out the class width, which, remember, that's just how far it is from one lower class limit to the next lower class limit. So to figure that out, basically find your biggest data value, your smallest data value. Subtract those two numbers, and then divide by however many classes or however many boxes you want. Now, this is going to be one of 2 times in this class you're going to hear me say, ignore standard rounding rules. So if you get any decimal point here, I don't care what that decimal point is, round up to the next highest number, to the next whole number. So always, always, always round up for your class width. So let's look at an example and kind of walk through this process. So what this data set is it's actually the commuting distance of 60 different workers, how far they drive to work every day to go to work in Dallas. And we want to build this frequency table. So I will always start out by giving you exactly what you see here. You're going to have this blank table layout. So you don't need to remember what goes in the frequency table. All you need to remember is how to fill in the stuff in the frequency table. So you need to know how to fill it in. You don't need to worry about knowing that you have to have class limits, class boundaries, frequency, a midpoint, relative frequency, cumulative frequency. You don't have to worry about knowing that you need those pieces. You just have to know how to calculate those pieces. So notice I said use 6 classes here. So first thing we have to figure out is how wide are each of those classes. So we need our class width. So your class width is always going to be the largest data value minus the smallest divided by number of classes, right? So if we look at this data set, we're just looking for the biggest and the smallest. So what is our biggest data value? So what is the furthest distance somebody drove into Dallas? 47. Yeah, so that's our biggest. What is the smallest distance somebody drove in? 1. Wouldn't you love to be that person? Only have to drive a mile to work. And then we're going to divide by the number of classes. So in this case, we wanted 6 classes. So I'm going to divide 47 minus 1 by 6. So if you plug that in your calculator, what do you get out? 7.667, right? So 7.6, and it's repeating forever, right? So we don't care. As soon as you see a decimal, no matter what, round up. So for us, we're going to let the class width be 8. All right. So I don't care if this was 7.002. If it's 7 point anything, no matter what, round up. So the reason why you're rounding up, if you were to round down, you would actually end up potentially not having a class for every single data value. So rounding down, you potentially make some data values not have a home. They don't have a box to go into. So that's why you always round it up. It just ensures every single data value will have a class no matter what. So from there, we want to fill in those class limits. So to start with the class limits, your first lower class limit, and we're always going to work with the lowers first. Your first lower class limit is going to be your smallest data value. So we just start with 1 because that was our smallest data value. So always start with your smallest data value. And then to get to the next class limit, add the class width. So here I'm going to add my 8. And that's going to tell me my next lower class limit, which is 9. And then I keep doing that process. So now I add my class width again. So I'm going to add another 8. And I'm going to get to 17. That's my next lower class limit. And I just keep doing that process. So we need 6 classes. So I add another 9, and I get to 25. Add another 9. Sorry, thank you. Add another 8 and get to 25. Add another 8, which is our class width, we get to 33. And add another 8 and get to 41. So each time here, I'm just adding that class width of 8 every single time to get the next lower class limit. Now I'm going to do something that might seem a little crazy. I'm going to go ahead and add one more 8 and go on down one more as if there was another class below here. So I'm going to go one more row down to 49. All right. That's going to seem crazy right now. It's okay. Just go an extra 1. It'll make sense why in a second. All right, so now we want the upper class limits. So let's jump back and look at that setup I gave you. Notice on this one, right, on this picture, with the class limits, right, there's no overlap. Why do you think there's no overlap there? So remember what we're doing here is we're taking that long list of raw data, right, so something like I showed you last week or 2 weeks ago now, but we're taking a long list of raw data and we're just putting it into boxes basically, right? So each of these classes, think of it like a box. So if there were overlap here between the different classes, you could potentially put something in two different boxes, right? So how would you know which class to put it in? So we do not want overlap. So because we don't want overlap, the way we're going to find the upper class limits is actually really, really simple. You're just going to take whatever the next class's lower limit is and subtract 1. And that's your upper limit. So here, this class is going to go from 1 to 8. Because I can't go up to 9, right? Because otherwise, they would overlap. So we just stop at the next lower whole number. And the ones I'm going to have you do, so you might see some on Hawks where it's not perfect whole numbers, just because of the way that Hawks generates the random data. So, but the ones I'm going to have you do will always be whole numbers, so you don't have to worry about decimals. So 1 to 8, you tell me, what's the next upper class limit going to be for that second class? 16, exactly. And then 17 to what? 24. 25 to what? 32. 33 to 40, and 41 to what? 48. So that is the reason why I went ahead and had that extra 1, right? So that now we can figure out, okay, well, if this one would be 49 if there were that class, then we have to stop this one at 48. All right. So now we don't need that extra 1 anymore. We don't care about it. It's gone. So we have our boxes. All right. So that's our class limits. So the next piece we have are the class boundaries. So basically what the class boundaries do, we're going to use the class boundaries whenever we graph these to account for the space between each class. So basically what we're doing with class boundaries is we're splitting that gap between every single class, basically. So right now, we've got that gap from 8 to 9, right? We've got a gap from 16 to 17. So we're basically splitting it in the middle to say, okay, we want to extend these boxes out as far as we can, technically, where they're touching. So for us, it's always going to be your lower class boundary is the lower class limit minus 0.5. And the upper class limit is always going to be the upper class boundary plus 0.5. So we're always going to add or subtract 0.5 depending on if it's a lower or an upper boundary. So we're just splitting that gap. And the 0.5 comes from the fact that 0.5 is half the distance of a whole number, right? So it's always going to be the lower class limit minus 0.5 to the upper class limit plus 0.5. Always. So here, my lower class boundary is going to be 1 minus 0.5, or 0.5. My upper class boundary for this first class, we add 0.5 to it. So it's going to be the 8 plus 0.5. So 0.5 to 8.5. So we're going to use the class limits as the actual boxes. The class limits are what we're using to put the items into the boxes, but these are what we're going to use to graph later on. So when we're actually graphing. So the limits are for boxing or for sorting. These are for graphing. And so you do that the whole way down. So my next class, so 9 minus 0.5, since it's a lower limit, which would be 8.5. And then 16 plus 0.5, since it's an upper limit, 16.5. Notice these two are the same, right? That's by design, because when we're graphing it, we want the classes to touch. So these numbers should be the same. But that also makes it a little simpler, right? Because now if you look and say, okay, this next number has to be the same as that number, right? So you don't even really have to do the math, 17 minus 0.5. You just know it's going to be the same number, so 16.5. Although if it helps you, absolutely, do the math every single time. So 16.5 to what? You tell me. 24.5, good. And so we just keep doing that all the way down. So 32.5 to 40.5, and then our last one, 40.5 to 48.5. I'm going to jump over to the class midpoint column now. So we use the class limits for actually sorting the data, for putting it into the different boxes. We use the class boundaries to graph the data. What we use the class midpoints for is to calculate with the data. So later on in chapter 3, we're going to talk about finding a value, a number to represent the middle of a distribution, or to represent a typical data entry. And we're going to talk about finding a number to represent how the data goes out away from that middle. So in this case, rather than using every single individual data value, you could use the summarized frequency table, but you would still need one number to represent that whole range of numbers. And so for us, we're going to use the middle, or the midpoint, to represent that. So to get the class midpoint, it's always going to be your lower class limit plus the upper class limit divided by 2. So it's just literally the sum of the class limits divided by 2. So for example, if I'm looking at the class 1 to 8 off of our frequency table we're working on, right? To find that midpoint, I would literally do 1 plus 8 divided by 2. So 4.5. That would be that class midpoint. Or for the next class, it would be 9 plus 16 divided by 2, which gives you 12.5. Now here's a little shortcut. Once you have one class midpoint, what do you notice about the distance between 4.5 and 12.5? How far apart are they? They're 8. They're your class width apart. So a little shortcut, rather than having to sit here and add up 17 plus 24 divided by 2, once you have one class midpoint, they're always going to be separated by your class width. So that means if I want to figure out the next one, I don't have to do 17 plus 24 divided by 2, right? I could just do 12.5 plus 8 and get to the 20.5. And then I can do 20.5 plus 8 and get to 28.5. And I guarantee you, you get the exact same result as if you sat there and did 17 plus 24 divided by 2, or 25 plus 32 divided by 2. It just falls out from the way we set up these classes. Makes sense, right? If each of these classes are the same width, which we designed them to be, then their middles are going to be the same width apart, right? And so on down, right? So 28.5, 36.5, and 44.5. So now it comes to the part of actually putting these data values into those boxes. So all you're going to do when you're doing that, it's kind of the same idea as when you were putting those data values onto your stem and leaf plot, right? So you would find the stem and then write your leaf down. So here we're just going to find the data value and we're going to put it in the class. So 13, where would 13 lie at? Is it going to be between 1 and 8, 9 or 16, 17 to 24, so on? Where would it be? 9 to 16. So I'm just going to throw a tally there. So the tally column's really just there to help you, as you're going through the data sets, figure out where it's at. So you don't have to sit there and go through and count every single number up here that's between 1 and 8. Try to find every single one at one time. So that's what the tally column's there for. It's just to help you, give you a place to kind of keep track of where each data value lies. So we go through 47, that's going to be down here between 41 and 48. 10, that's going to be between 9 and 16. And so we go through and we do that for every single data value. Now I'm going to cheat a little bit because I know what these should be. All right, so we've now gone through that process of tallying up every single data value. So we have our tallies, which just count up how many of the data values lie in each class. To get your frequency, you just count the tallies. So to get your tallies, you're just going through and just putting a slash mark wherever each of those individual data values are. So for example, for 13, I put a tally in 9 to 16 because that's where 13 lies. For 47 was down in that last class. The frequency is literally the count of the tallies. So how many of the data values actually lie from 1 to 8? 14, exactly. That's your frequency. 21 lie between 9 and 16. 11 lie between 17 and 24. So you're literally just counting your data values. And then 6, 4, and 4. So at this point, you actually have it's a good point to stop and check yourself. Make sure you didn't miss any data values. So add up all of your frequencies. So you're going to see me use this little sigma. It's the capital Greek letter sigma. You're going to see me use that to represent sum. This just basically means the sum of the frequencies. So add up every single frequency. You get 60. You think that's a fluke? We had 60 data values, right? So this should add up to however many data values you get. This should add up to your N, your sample size. If it doesn't add up to 60, that means you've messed up somewhere. Go back and check your tallies and your frequencies. So that's a quick check. It's not going to tell you if you put every tally in the right box, but it's going to tell you if you either missed something or counted something twice. So it's a quick way to check yourself in that respect. So relative frequency is just the proportion of the data values that lie within that class. So to get relative frequency, it's always going to be just frequency divided by n. It's basically converting it to a decimal or a percentage. So here, for example, for that first class, to get my relative frequency, it would be 14 out of 60. And we're always going to use preferred decimals in this class. So you would actually go ahead and do the 14 over 60, convert it to a decimal. And let's just say to 2 decimal places for the sake of this. So when we do that, we get 0.23. So that tells us that there's that 23% of your data values are going to lie somewhere between 1 and 8. So the next one, we had 21. So 21 out of our 60 data values lie between 9 and 16. And so we do that, and we get 0.35. So the reason why we calculate these relative frequencies, it's going to come back again in Chapter 4 when we start talking about probabilities. But also, so probability aside, it also just helps us if we want to compare across different data sets. So maybe we have the data for Dallas, which is what this data is, but then we also have the data for Charlotte. You can compare and see, do people live closer to Charlotte than they do Dallas, for example? Or do people commute further to go to work in Charlotte than they do Dallas? So it lets you compare easy. It lets you compare more easily among data sets. Because otherwise, if you just look and say 21 people live 9 to 16 miles from Dallas, and then 121 people live 9 to 16 miles from Charlotte, well, you can't really compare that because you don't know how many people were in each sample. But by putting it into the relative frequency, everything's going to be out of 100, basically. So it's always going to be as a decimal, which we can compare easily. And so same idea, right? We just go through, so 11 out of 60, and we get 0.18. 6 out of 60, we get 0.1. And then 0.07, 0.07. Here's another place to stop and check yourself. So we know the sum of the frequencies is always going to be 60, your sample size. What do you think the sum of your relative frequency should be? Should be 1, right, which is the decimal representation of 100%, right? So if we've accounted for everything, it should add up to 1. or very, very, very close to 1. So because we're rounding these decimals, it might be something like 0.997 or 1.002. That's fine. As long as it's close to 1, we can accommodate that rounding error and know that it's still close enough. If you're getting some of your relative frequencies that's 0.87 or 1.5, you've probably done something wrong somewhere. Go back and check your frequencies or your relative frequencies if your frequency's checked out, right? But it's another spot to check. Make sure you haven't messed up somewhere. And so the last column, cumulative frequencies. So this one, think of this as basically your running total. So it's kind of your running total of how many data values you've gone through at each row. So it's always going to be the sum of the frequency that you're on for that class and every single class above it. So your first class is really easy. It's always just going to be the same as the frequency. Because there are no other rows to add to it, right? So now we go down. So our next one, well, we want the running total, so we're going to add the 21 to the 14. So that's going to give us the 35. So we've gone, at that point, we've gone through 35 of our data values. So then now, for our next one, same idea. We're going to add the 11 to the 21 and the 14. Now, have we already added 14 and 21 though? We have, right? So we can use that to our advantage. I'm not saying you have to sit here and keep adding more and more and more numbers. Really, all you have to do is just add to your previous cumulative frequency, right? Because we've already added every other row up. So for this next one, all you have to do is 35 plus the 11 to get to the 46. And then same idea. So our next one, you tell me, what two numbers are we going to add? 46 and 6, exactly, to get to 52. And then now, same idea. Add 52 and 4 to get to 56. And then add 56 and 4 to get 60. One more place to check yourself. Notice this is n again, right? It should be n again. Your last cumulative frequency should be the total number of data values because you should have gone through every single data value, right? So that's one more place you can check yourself, make sure you haven't missed a data value somewhere. All right, so the last piece of this section is talking about histograms. So basically all the histogram is a picture of that frequency table. So it's putting it into a picture. It's taking that table and putting it into a picture. So basically a frequency histogram, it's a bar graph. But it's a bar graph representing that table that you have. So across the x-axis, it's always going to be quantitative, and it's going to represent the data values. So for us, that x-axis is always going to be the class boundaries. So we're going to keep it simple. We're always going to put the class boundaries along the horizontal axis. Now, if you're looking in your book or if you look at some stuff online, so say you Google this, you might see some stuff that says use class midpoints. So with technology especially, a lot of times it's going to try to use class midpoints. For us, we're always going to use class boundaries. And your vertical scale is going to represent frequencies or relative frequencies. So on a frequency histogram, it's just the frequencies. If I say a relative frequency histogram, it's the relative frequencies. So that's the only difference between if I say a frequency histogram or a relative frequency histogram, is what goes on the vertical axis. Otherwise, they're the exact same. Now, if I just say histogram, assume I say frequency histogram. So by default, it's typically going to be just the frequencies on the vertical axis. So if I don't say frequency histogram, if I just say histogram, it's really a frequency histogram. If I want a relative frequency histogram, I will specifically flat out say, give me a relative frequency histogram. And there really is no advantage to using frequency or relative frequency histograms other than if you're comparing against other data sets. So that's kind of the same reason why we wanted those relative frequencies in the first place, right? Is because it's easier to compare. So the same thing is going to be true when it comes to frequency versus relative frequency histograms. But when it comes to just looking at the shape of that distribution, which is normally what we're going to use these for, it makes no difference whether you calculate a frequency histogram or a relative frequency histogram. You're going to get the same picture. So the widths of the bars are your class width. So all those bars will have the same width. And then the bars have to touch, which is one reason why we're using class boundaries. It kind of eliminates. So if we use class midpoints, what I've found a lot of times is people forget to make the bars touch. If you're using class boundaries, it kind of forces those bars to touch. So if we go back to that example we just did and look at that one. So say we wanted to make a histogram for this. So you're going to put your class boundaries along the bottom, but basically think of this x-axis, this horizontal axis, think of it as a number line. So one of the biggest mistakes I'll see people do on this is they might write 0.5 to 8.5 and then 8.5 to 16.5. Don't do that.
So it'd be like 1, 8, whatever the number is on the left.
Yeah, well, be careful. We're going to use the boundaries, but it's going to be exactly that. So it's going to be, think of it like the number line. So 0.5, 8.5, 16.5, and so on that way. So each number just shows up once. So it's just like a number line. And then you want to give it a title. So think of those pieces that we said you had to have in section 3, right? In 2.3. You have to have a descriptive axis title. So here I'm going to say commuting distances in miles. Right? So something so that if somebody only had this picture, they know clearly what this represents. And then your frequencies go along the vertical axis. Now for your vertical axis label, frequency is an acceptable axis label. And so we kind of go up from there. So I'm just going to count these off by fives. So 5, 10, 15, 20, 25. And then you're just drawing the bars for each of those classes. So 0.4 or 0.5 to 8.5, so that class 1 to 8 had 14 data values. 8.5 to 16.5 had 21. And so on down. So we had 11, 6, 4, and 4. And then the last piece, add a title. So commuting distance to Dallas, for example. All right. And that's all there is to a frequency histogram. The only difference between this and a relative frequency histogram, you would have, instead of frequencies going up, you would have relative frequencies. That'd be the only difference.